If we have a beam that consists of many spectral components, there's various dispersive elements available which we can use to split those spectral components apart. For instance, using a grating, we can disperse the light across a CCD array for spectrometry, or across a spatial light modulator for things like spectral pulse shaping, filtering, switching, etc. We can also use the grating in the opposite way to combine multiple spectral components into a single beam. For polarization, there's also many ways in which you can split a beam up into its orthogonal polarization components, like polarizing beam splitters, birefringent crystals, that kind of thing. So for both wavelength and polarization, there's a lot of options available, some that have been around for centuries, that allow us to manipulate a light beam in the wavelength and polarization basis. What about the spatial properties of light? Discounting the trivial cases where you just want to split the beam up into a bunch of non-overlapping sections, when you could just use an array of points to sample it, like a CCD camera or fibre array. What if you have a beam that consists of many spatial components, like say the modes of a fibre, and you want to split them apart? A beam that consists of many orthogonal spatial components where all the spatial components are more or less on top of each other, right, overlapping in space. For that task, there are limited options, and they're options that have only been invented relatively recently. So one is a photonic lantern. Photonic lantern is a multi-mode to single-mode transition. It's a tapering of an n-mode multi-mode fiber on one end into n single-mode fibers on the other end. So it's a full three-dimensional refractive index profile. It's a lossless device whereby a spatial mode put into one end gets split up and decomposed into its individual spatial components as diffraction-limited spots on the other end. The photonic lantern was originally invented for astronomy, where light is collected by the telescopes into a multi-mode fiber before being sent to single-mode spectrometers. The all-fiber construction of a photonic lantern is both its main benefit and also in some applications its main drawback. Ultimately, the type of devices you can make with a photonic lantern are limited by the kinds of fiber devices that you can actually manufacture. The second option is a multiplane light conversion system, MPLC, and that's what I'll be talking about today. It's a bit like a discrete version of a photonic lantern. Light propagates through successive phase plates separated by free space propagation, which allow light to be transformed from one spatial basis to another. Like the photonic lantern, this device is also just phase manipulation, so it's lossless, but it's capable of more easily implementing arbitrary transformations, as it's not constrained by the same limitations of what you can actually manufacture as a tapered fiber device, right, like the photonic lantern is. Calculating the phase masks required to implement this conversion can be done by using the masks to match the phases of the input and output mode sets at each plane. So ultimately, if we want this device to actually work, we need the modes in one direction to match the modes in the opposite direction. They need to be the same. So to start with, we propagate each of the input modes from the source to the first plane. Then we propagate the output modes backwards through the system to meet them at that same first plane. To calculate the phase mask we should use for that plane, we perform the spatial overlap between each pair of input and corresponding output modes, and we sum all of those overlapped fields for each pair of input and output modes together. Then we take the phase of that superposition, and that's our new phase mask for that plane. Then we propagate to the next plane and do the same thing. Overlap the forward and backward modes, sum their overlaps together, and then take the phase of that superposition as the new phase mask. And like that, you work your way through the device, through each plane. Then when you get to one end, you flip it around and propagate back the other direction following the same process. So we can see from this demo here that even after just one pass back and forth, it's already started to match up quite well. Now there's lots of little tweaks and optimizations and additional constraints you can apply and should apply to the algorithm to make it work well, but this is the basic idea. In practice, the fewer phase mask planes you can get away with using, the better, for several reasons. First, is because it makes it smaller, cheaper, and easier to actually make the thing. And second, because these MPLC devices are theoretically lossless, but in practice, the loss is going to scale with the number of optical surfaces that the light has to travel through. So let's say that each plane has 0.1 dB of loss. That's pretty decent, But if you've got 100 planes, now you've lost 10 dB and 90% of your light. So how many planes do you actually need for a given transformation? Well, it depends what the two spatial bases are that you're trying to convert between. Some are easier than others. So in the worst case, if you're converting between two bases, each a set of n orthogonal modes, then at most you'll need 2n planes. But then if you want that system to work over a more extended bandwidth, then you'll need to add more planes to make that transition smoother and more adiabatic. Because the more you diffract the beam with your masks, the more wavelength dependent it's going to become. So you want to be smooth. Eventually, if you added an infinite number of planes, you'd have a completely adiabatic device that's kind of like a photonic lantern now, which naturally has high bandwidth. So we can see that if we're converting a basis of like 45 modes and we were to need 90 masks plus maybe some extra ones for increased bandwidth, then suddenly most of our light's gone, right? Even for this theoretically lossless device. But we also know that not every basis transformation requires that many planes, and not every basis transformation's number of planes even scales with the size of the basis. So for a simple example, if we want to convert between the XY position real space basis and the K-space angle basis, from that we just need a lens, right? Or in fact, you don't even need a lens, you could just use free space propagation, right? That gives it to you for free. So in that instance, you need, depending on how you define a plane, either no planes, one plane, or two plane. But that's a fixed number that's independent of the size of your basis. So in fact, this basis is completely continuous anyway. Well, here's another easy one. We've got an array of spots, and we just want to rearrange those spots. For that, you just need two planes. One plane to tilt the spot in the right direction, and then one plane to stop the spot from going any further once it actually gets there. Again, as long as you've got enough pixels, the number of planes required doesn't scale with the number of spatial modes. It's always just two. Now that's a pretty easy one because all the spatial modes don't overlap at all in either plane, so they're completely separate. But here's another example where we're converting between two orthogonal bases where all the different spatial components overlap. So we've got a Hermite Gaussian set, can be converted to a Laguerre Gaussian basis just using a pair of cylindrical lenses. One lens to start the transformation and one to stop it and keep the beam round. Again, this doesn't scale with the number of modes, it's always just two planes. It works because all the modes, regardless of how many modes there are, all need the same thing for this transformation to occur. They all need a phase shift to be introduced between the X and the Y component, right? And a cylindrical lens focusing on one axis but not the other gives one axis a Gauss phase shift and the other one nothing. So not every basis transformation requires a full 2n number of phase planes, and some don't even depend on n. In this work, we're interested in perhaps the most common transformation type required in both optical telecommunications and also astronomy, splitting the modes of a multimode fiber into an array of single-mode fibers. But within that, we've got flexibility regarding exactly what maps to what, right? We just want a lossless, unitary transformation. Everything else is negotiable. We don't necessarily care what the shape of the single mode fiber array is, the geometry of the single mode fiber array. Ultimately, it'll be easier in practice if it's a linear array or a rectangular or square array or some sort of densely packed array like a triangle or a hexagon. But we can always just add a few extra planes at the end to remap the shape of the array itself if need be, as long as the overall solution is low loss and low plane count. For a given array geometry, we also don't care which fibers map to what modes. Right? We don't care about the ordering of the array. So we don't care about array shape or geometry, and we also don't care about the order. So those are design degrees of freedom. We also generally don't care what orthogonal set of modes the single mode fiber maps to. It could be something like Laguerre Gaussian, which closely resembles the fiber eigenmodes, but it could also just be a complete scrambling of modes. Astronomers don't care what the mode mapping is, and in telecommunications we generally don't care either, because over long lengths of transmission fiber, the modes are going to couple anyway, regardless to how you put them into the fiber in the first place. So with this in mind, we set out to try to make the laziest possible MPLC device. A device where each phase mask needs to do as little as possible, converting from an array of single mode fibers to a mode basis which was as close as possible to that original array of spots, but an orthogonal and complete set. So we start off with the spots arranged in this concentric circle pattern. This geometry was originally used in mode division multiplexing before ultimately being replaced by photonic lanterns. It's an array geometry which minimizes the mode dependent loss for a given number of modes. Each one of those spots excites a superposition of modes in the fiber basis, which looks a lot like a spot, but isn't actually a Gaussian. It's got some other features to it. The closer you get to the edge of the fiber core, the less Gaussian those spots look, and also the more loss you get. But they're always quite localized spot-like distributions. So this fiber array to fiber mode transformation isn't lossless, and some spots have more loss than others. We don't want that. We want a lossless, complete orthogonal set. So let's make one, using this as a starting point. To do that, we can take the coupling matrix between the spot basis and the fiber basis, the overlap between each mode and each spot. We can then use the singular value decomposition to split that non-unitary matrix, the coupling matrix, into three components: a unitary transformation of the input basis, U, a unitary transformation of the output basis, V, and a non-unitary diagonal matrix of the singular values. So these represent the transmission coefficients for each modal component through the system. And these are what we want to be unitary. We want them to all be the same. If you look at these singular values, we can see that we've currently got about 7 or 8 dB of mode-dependent loss going from the spot array to the fiber modes. So mode-dependent loss is the ratio between the maximum and minimum singular value. So we just force all those singular values to be 0 dB, no loss, and then put the matrix back together again. So now we've got a coupling matrix that looks a lot like the old matrix, except now it's orthogonal. Right, we got that original coupling matrix, and we converted it to the nearest orthogonal basis. Now if we use this new basis, we get localized spot-like modes, but they form a complete orthogonal lossless set, which is great because it should be easy to convert between our 2D single mode fiber array and these spot-like modes because they're almost the same and they don't really overlap much in space, right? They're almost independently localized. So let's have a look at a solution. Here we have 45 modes implemented with just less than n divided by 2 planes, so 22 planes. The y-axis here is the propagation direction. Far left column is the sum of the intensities of all modes, just like a summary. Second from the left is the phase masks that do the transformation, and the rest of the x-axis illustrates each of those 45 modes individually as they evolve through the system. Alright, so let's have a look at the evolution of these spots through the whole system. Another perhaps more intuitive way to look at it is to arrange the evolution of the modes into the shape of the original array. In all these you can see that the spots get focused and refocused once near the start and also once near the end. That doesn't necessarily have to happen. These aren't unique solutions. It kind of depends on what your starting mask scenario was. But that is a solution which works quite well, and it keeps the light from falling off the edge of the mask over the course of the 22 planes, right? Keeps it focused. But the evolution is also somewhat disappointing and unsatisfying. It does go through all those planes, does all these sort of fancy theatrics along the way, only to return to something which looks almost the same as what it did at the start. There are also other solutions which keep the spots much more spot-like throughout the entire transition, but don't necessarily give you any less planes or any less loss. So if we look at the performance of the transition, we can see it does have good insertion loss. Insertion loss is the average singular value from before. It represents the average loss over all possible spatial paths through the system. It's also got decent mode dependent loss for a 45 mode device of about 2.2 dB and quite good bandwidth and flatness. because each mask isn't doing that much. So the device is performing well, better than most MPLC devices would for a spot to fiber mode conversion. But ultimately, there's an even better mapping that we can employ. What we can do is just take the positive quadrant of a grid of spots in the XY plane and map the XY positions to the XY indices of the Hermite-Gaussian modes. This mapping greatly reduces the number of planes required for the conversion, which we'll see in a second. But it's also an excellent mapping in the context of graded index multimode fiber, because each Hermite-Gaussian mode consists of a superposition of near-degenerate fiber eigenmodes. So ideally, each HG mode, each Hermite-Gaussian mode, consists of a superposition of fiber modes with almost exactly the same propagation constant and group delay. So modes within these mode groups couple heavily in a multimode fiber anyway, almost immediately. So for high quality graded index fiber, exciting a Hermite-Gaussian mode is about as mode selective as you're going to get in practice anyway. It's also good because a triangular fiber array is something that's not too difficult in practice. It's a densely packed array, so that you could just use something like a slice of a hexagonal fiber array. Looking at a solution example here, we can see that the transformation has been performed quite well using just 7 planes. Same design parameters as the previous example for the spot basis, except I have doubled the resolution of the masks in X and Y. That's not a necessary point. It's just that if you've got less planes, it frees up some computational complexity and memory to spend on resolution, if you wish. But it does make a big difference. It's not a number of pixels thing. So if we zoom in, we can take a closer look through the short transition for each of the first few fiber modes, and then for all 45 of the modes. In terms of the performance, it's a bit worse insertion loss and mode dependent loss, and not quite as wide bandwidth compared to the quasi-spot example from before. This is a quick little demo simulation. You could optimize that a bit more, center the response a bit better for the mode-dependent loss. But ultimately, the point here is that we've used less than a third of the number of planes. 45 modes in 7 planes, and got a sort of comparable level of performance. If we have a look at the transformation for a 45 mode example, a 15 mode example, and a 6 mode example, all with the same basic design parameters other than the number of modes in the set, we can see similar features of the transformation. So it starts off as the array, becomes this V formation, or a bit like X-like if there's only a few modes, with stronger intensity on the XY axis and at the axis origin. This then flips to the other side, starts to have this more X-like distribution with light in all 4 quadrants. That evolves into this thing which looks a bit more like a tick or a bird, depending on the solution, with a sort of semicircular body in one dominant quadrant, 2 rectangular legs / wings on the top and bottom quadrants, and then a little head in the left quadrant. So the details can change a bit depending on the exact solution. Again, it depends on things like the starting conditions, the number of planes, design parameters, etc. But it always has that same general form to it. So what exactly is it doing? Well, I don't have a rigorous mathematical answer for you, unfortunately, but it seems to be exploiting the symmetry of the modes to achieve the transformation in a very limited number of planes. If you look at the symmetry of a Hermite-Gaussian mode, it's symmetric in both X and Y. If you look at the locations of the dominant lobe of a Hermite-Gaussian mode, they're organized in this triangular semicircle-like pattern. Which looks a lot like our original triangular array shape, and also the shape the array ends up being manipulated into during the transition. So if that array is duplicated in X and Y, that gives you the 4 main lobes of the Hermite-Gaussian mode. My guess at this point is that's what it's exploiting to enable it to perform the conversion with very little dependence on the number of modes and the number of planes required. Right, all modes need the same thing. They need to be duplicated in X, and they need to be duplicated in Y. Because all the modes need the same thing, you need less planes. Okay, so we've started here with a triangular array, which sometimes will be fine. Again, it's just a triangular slice of a densely packed hexagonal fiber array. But it'd be even better if it was a 1D fiber array, because that makes it, obviously, they're very easy to come across. You can get arrays, 1D arrays, which are very tightly spec'd in their tolerances. And it also makes it easier to get little micro lens arrays for collimating the spots onto the first plane. But the important point here is that we've got a good solution as our starting point. So now it's not a big deal to remap from a triangular array to a linear array using additional phase masks. And there's two ways you could go about that. You could do sort of two separate problems. Do a set of masks for the triangular to Hermite-Gaussian transition, then another set of masks for the linear to triangular transition, and then just paste the two solutions together and optimize it a bit more. Alternatively, you can just evolve the shape of the array as the simulation itself is running. So here I've just started off from the triangular array, got a decent solution, and then I've opened up that array into a line, keeping the symmetry of the array the same all the way through, until you get to the last set of modes in the center. So the Hermite-Gaussian modes, where the M and the N indices are the same. So these are the sets of modes which don't have a symmetric 90-degree rotation version of themselves like the other modes do. They're all on their own, right? So that's just a final optimization step at the very end where you break that symmetry at the last possible moment to get your final linear array. And then you can perform a few extra little tweaks, etc., to try to eke out some better performance. But ultimately, the solutions we're going to be looking at here are use 14 planes rather than 11. That's largely just to do with the manufacture of the phase plates itself. But more planes gives us a bit better performance, but it also helps more with the bandwidth. So more planes means it becomes a bit more adiabatic. It's a smoother transition, smoother phase masks, less diffraction per plane, which means more bandwidth. And we can see in the solution here for the 14 plane implementation that most of those extra planes actually just end up being used in the spot remapping section of the transition rather than the Hermite-Gaussian conversion part of the transition. It's actually the spot rearrangement part which hurts you the most bandwidth-wise, as that's the bit where the light's trying to be steered across a bigger angle. Right, you're trying to steer the light from out wide right into the center of the beam. And it's usually these outer spots on the edges of the arrays. They have to travel the furthest distance, which is also the biggest constraint on your bandwidth. So we can see that given the option, the algorithm has actually distributed more planes to the spot transition rather than the Hermite-Gaussian transition to give us more bandwidth. And we can see that the Hermite-Gaussian transition itself has that same basic form. It's just a bit more spread out over a couple of extra masks. Again, an interesting way to look at the evolution of the light through the system is to arrange each mode's journey through the device into the shape of the original triangular array itself, although now we're actually starting from a line, but still. All right, so we can see it starts off. It's all mostly just rearrangement of the spot array itself. Then we get into the business end. We can see that all the modes focus into different sized and different XY portions of that same V shape with the bright spot on the axis origin. The outer X and Y dominant lobes kind of fly off by themselves and then wait for the rest of the mode to diffract out and meet them to form the complete mode. In terms of the performance itself, we can see that the insertion loss is good. We've got about 1.5 dB of insertion loss that's pretty flat over 100 nanometers. And we also get very good mode dependent loss. This is 1.3 dB to 1.7 dB across that same 100 nanometers of bandwidth. And again, 1.3, 1.5, 1.7 dB of mode dependent loss for a 45 mode device, even theoretically, is very good. And especially given the few number of planes it requires. All right, so that's it. So we've shown that using either a quasi-spot-like basis, or particularly using a Hermite-Gaussian basis from a triangular fiber array, we can significantly reduce the number of planes that are required for a multiplane light conversion system.